Artemis 2 rocket must gain speed second by second to escape the Earth's gravity and reach the Moon. Every push from its engines adds momentum, carrying mass higher and faster. The simple principle of momentum is what makes space travel possible. But to achieve interstellar travel and reach faster than light speeds, we must completely reimagine our understanding of momentum. Let's start with the simple, familiar momentum that we learned in classical physics. In classical Newtonian physics, momentum is one of the simplest and reliable concepts. It is defined as mass times the velocity. Momentum grows proportionally as speed increases. There is no upper limit, no special speed, and no paradox. The equations behave exactly as our everyday intuition predicts. At the start of the 20th century, Einstein showed that Newtonian momentum fails at very high speeds. Momentum must account for the structure of spacetime itself. As the velocity approaches the speed of light, momentum increases dramatically. Particles can get very close to the speed of light, but they can never reach it. Here's the paradox that has faced physicists for over a century. If momentum becomes infinite at light speed, what would happen if a particle somehow crossed that barrier? Most physicists stop here and declare the problem meaningless, but the decision is philosophical, not mathematical. If we try to extend Einstein's momentum formula beyond the speed of light without changing anything else, the math breaks down. The square root in the Lorentz factor changes sign. Momentum becomes imaginary, signaling that the equations no longer prescribe physical reality, suggesting something fundamental is missing in our understanding of superluminal motion. In the 1960s, physicist Gerald Fennenberg investigated this problem and proposed tachyons, hypothetical particles with imaginary mass that could travel faster than light. While mathematically intriguing, tachyons introduced serious physical issues, including instabilities and potential violations of causality. Most physicists concluded that faster-than-light motion was unphysical, yet the concept inspired decades of thought experiments in theoretical physics. What is rarely questioned is why spacetime is allowed to stay rigid while everything else adapts. That assumption is so deeply baked in that most people never notice it. General relativity teaches us a crucial lesson. Forces like gravity are really expression of spacetime geometry. Particles move with the way they do because geometry tells them how. Changing the metric changes the rules of motion themselves, opening the door to new ways of understanding superluminal motion. Instead of modifying mass or accepting imaginary quantities, let us allow spacetime itself to respond to velocity. As a particle accelerates, let's assume that spacetime stretches or compresses in response. This keeps momentum real even as velocity approaches or exceeds the speed of light. By letting a geometry adapt, we create a consistent framework to describe motion across subliminal, near light speeds, and superluminal regimes. At this point, we have two options to consider. Either that faster-than-light motion is forbidden forever, or that spacetime itself must respond to its motion. With this historical and geometric foundation, we are ready to define a velocity-dependent line element and derive momentum directly from the structure of spacetime itself. Imagine a particle moving faster than light. That seems impossible, right? Normally, physics forbids it, but today we're going to explore how we can describe such particles consistently using a velocity-dependent function that stretches spacetime itself. In the next 15 minutes, we will carefully derive the momentum of both relativistic and tachyon particles step by step and reveal some surprising counterintuitive behavior. Most treatments of tachyons quietly fail by allowing imaginary momentum. Today we will not do that. If you believe fast-light motion is impossible by definition, the following derivation will probably make you feel uncomfortable. We start with the concept of the line element. This equation defines the square distance between two infinitesimally close points in space-time. The metric tensor G sub AB, which determines how distances in space and in time intervals are measured. The metric tensor A sub B is a rule which determines how distances in space and intervals in time are measured. The second two terms in the line element correspond to differential directions along a coordinate, like x, y, or t. Understanding this metric is essential because it tells us how space-time is shaped, especially when particles move at high velocities beyond the speed of light. To incorporate faster-than-light motion, we introduce a velocity-dependent scaling function f(v). Using the Einstein summation index and expanding terms, the line element is fully written as the function f(v) times the square of the differential in time and the function f(v) times the differential in z squared, with dx and dy being unchanged. As we journey through the cosmos, every motion, every push follows the rules of physics. Even in empty space, momentum is always at work. Go ahead and subscribe for more cosmic journeys as we discuss faster-than-light travel further. Why do we need the function f of v? In normal relativity, velocity is bound by the speed of light. But if we want to model particles that exceed c, the speed of light, then space-time itself must adjust the equations. At low velocity, f of v is equal to 1. Critics will say this function is ad hoc. That criticism misses the point. Every metric choice is ad hoc until the experiment justifies it. Special relativity made the same move, it just did it earlier. Here, m0 is the invariant rest mass and v is the velocity. This form combines standard relativistic effects with the velocity-dependent metric factor f of v. Let us analyze the motion in both subluminal and superluminal regimes. This captures proper time along the particle's path. For tachyons and relativistic particles, we can expand the Lagrangian using the Einstein summation index. Next, we'll define the Lagrangian for the particle's motion. The general form is written at the square root of the metric coupled with the velocity terms. This gives us a clean starting point for computing momentum explicitly. Substituting our Lagrangian into the derivative and factoring out the constants, the momentum reduces to the following form. Canonical momentum is defined as the derivative of the Lagrangian with respect to velocity. This step separates the outer square root from the inner function. Next, we'll expand the inner derivative using the product rule. We'll apply the chain rule for the derivatives to the square root term to get the following equation. Applying the product rule to the inner derivative, we can get the expanded equation in the following form. Next, we'll take the derivative of the first term, which is the minus 2 times the velocity, divided by the speed of light squared. Substituting this derivative back in, the full expression becomes as follows. This accounts for how both the standard and relativistic terms and the velocity-dependent metric contribute to the overall momentum. Going back to our original equation, we can now substitute the solution back into the original formula for the momentum and we can get the final form. Simplifying, we can separate the equation into two parts. The first term dominates in most cases, while the second term explains the subtle effects of tachyon motion. Things can simplify by rearranging the terms. We can now write the canonical momentum equation in the following form. We'll call this the universal momentum equation. The first term represents the standard relativistic momentum effects, modified by the velocity-dependent factor of Fv. The second term catches the effects of how spacetime stretches or compresses as velocity changes. This term is especially important for tachyons because it can reduce the momentum even as the velocity increases. By carefully analyzing both terms, we can predict the behavior of particles at subluminal speeds, near light speeds, and superluminal regimes without breaking the equations of motion. Now, let us define the step function f of v, which controls how space-time responds to the particle's velocity. For low velocities, the function f of v is equal to 1. This reproduces the standard equations in special relativity. Near the speed of light, the function f of v is approximately a slope or a gradient across the light barrier for large values of sigma. We'll label this term f of c. At superluminal speeds, or faster than light speeds, the function f of v is approximately -1, which ensures that the equations remain mathematically consistent for tachyons. This function is essential for understanding the counterintuitive behavior of momentum at extreme velocities. Here comes the surprising part. For superluminal speeds, the derivative terms of f of v can dominate the behavior, causing the momentum to decrease as velocity increases. This is counterintuitive because normally faster than light particles carry more momentum. At subluminal velocities, the momentum grows normally. Near light speed, the momentum will rapidly increase to a maximum value, but not an infinite value. It becomes finite. For superluminal velocities, the momentum will decrease as the particle speed increases. Mathematically, this is fully consistent with our Lagrangian and the velocity-dependent metric. Physically, it tells us that tachyons behave in a way that seems very strange, but is entirely predictable by the equations that we've derived. If this feels wrong, ask yourself whether intuition has ever been a reliable guide at relativistic scales. Leave your thoughts and comments below. I would love to hear what you have to say. If the gradient f of v is small, we can neglect the second term of the gradient of the function with respect to velocity and set it equal to 0. This will help with the rest of our discussion. The momentum simplifies to the invariant mass time, the velocity multiplied by the square root that accounts for relativistic corrections. This is where interpretation splits. Some see a natural cutoff, others see a red flag. Which one you see says more about your assumptions than the math. Every flyby, every maneuver is a balance of speed, direction, and force. These same principles govern the behavior of faster than light particles theoretically. Let us return to subluminal speeds. Remember that f of v is equal to 1. This gives us the standard relativistic momentum found in special relativity. At luminal speeds, or light-like velocities, we get f of v is equal to f of c, which is approximately a slope or gradient across the light barrier. This means that momentum has a critically large value, but not an infinite value, presumably on the order of the Planck scale. The last regime we'll talk about is for superluminal speeds, or faster than light speeds, where the function f of v changes sign. It is now equal to -1. This creates a counterintuitive behavior where momentum can actually decrease with increasing velocity. The universe may hold shortcuts, but all motion is ultimately governed by momentum and geometry, whether real or theoretical. Let's summarize what we've learned. We started with a velocity-dependent line element, introducing the Lagrangian for relativistic and tachyon particles, and derive the canonical momentum. Recall, the step function f of v controls how spacetime stretches with velocity as it reacts to a particle's motion. We derive the universal momentum. Recall that the first term is the standard relativistic momentum modified by the function f of v. The second term explains the tachyon behavior as particles transition the light barrier. Subluminal speeds behave as expected. Near light speeds are enhanced, and superluminal speeds exhibit counterintuitive momentum and reduction. Nothing here violates relativity, only the assumption that space-time refuses to participate. To visualize it intuitively, imagine space-time as a stretchy fabric. Low velocity particles glide normally. Near light speed, the fabric stretches and increases effective momentum. Superluminal particles push against the fabric so much that the stretching reduces their momentum. This analogy helps us understand how f of v, the step function, governs momentum crossing all velocity regimes making the strange behavior of tachyon particles predictable and mathematically consistent. In the next video, we'll explore what happens if we actually accelerate a particle beyond light speed and watch the momentum evolve in real time. You'll see tachyons in action and how our equations predict their motion precisely. If you enjoyed this derivation, make sure to like the video and subscribe to my channel and comment with your questions. Click the next video to continue exploring the fascinating physics of faster than light travel.